Okay. So in the last class, we spoke about body transconductance. Okay, and we almost spent an hour for this in order to see the physical phenomena, and later we translated that into a large signal, and from there we modeled the small signal. Okay, so we went around a very long path, and now today we just want to compute few things. One of the major things that today we'll be addressing is the output impedance calculation, and the second one is the transconductance calculation. Okay. So these are the two major points that we'll be discussing today, and before that I just want to motivate like why we need to identify these two parameters for a given circuit. Okay, so whenever you take any kind of circuit, it could be a single stage or a multi-stage or even a differential pair, our main focus would be on the gain, right? So this is the major focus or interest that we will put on a circuit. Now from the last example, like say for example we had discussed about a common source amplifier with a resistive load. Now this resistive load had a gain expression. So what was the gain for this CS amplifier with a resistive load? What was the result? We got it. So if you remember, this is our CS amplifier. If at all, if I have a resistive load as RD and composite signals at the outputs and inputs. Okay, yeah. So for this circuit, what was the we also stated lambda is equal to 0. So due to which we had a gain which is defined as minus GM times RD. In general, we have two components. One is the transconductance. The other one is nothing but our resistance RD. Sorry, it has. Yeah, fine. Okay, so there are two components, and that is the reason why we are looking for this output impedance and the transconductance of a given circuit to be evaluated, such that what happens is that in general I can write any of the circuit's gain as something like a product of transconductance into the output impedance. So now this RD is nothing but the output impedance of the circuit that I am using, and this GM is nothing but the transconductance of this device. Okay, so in short, for any circuit I can write something like this, the gain expression. Now our goal is to figure out how to evaluate this R out for any kind of circuit that I have given, and also try to figure out how to compute the conductance of the circuit. Okay, so once I know these two values, I just multiply both these quantities in order to get the gain expression. Is that clear? So now let me first talk about this output impedance. Calculation. This is something like the computation of an impedance of a circuit seen from a specific port. Okay, it could be either from the output or input, whatever it is. How to compute an impedance of the circuit seen from a specific port is what I'm trying to define here. So there are a set of rules that I will write it. So what you need to do is that, say for example I have a two-port network, and let us assume that this is my output node, and what I'm supposed to do is that the very first thing that I need to do is to connect a voltage source Vx across this output node or any pair of terminals. Okay, and once this is done, the second step is to suppress any independent sources that I have. Okay, so in general, in case if my circuit has my Vn, this Vn has to be killed first, okay, before I really begin evaluating it. So how do I kill this Vn? Yeah, short this particular node. Okay, so let me write both these quantities. So connect a voltage source Vx to the port where you exactly want to identify the impedance. The second point is to suppress all independent sources. Okay, so now when I say independent sources, a Vn is something related to that. Okay, And the third one is to measure Ix and use that Ix to calculate something known as Rx, okay, so which is defined as Vx by Ix. Is that clear? So now this Ix is a current that goes from this Vx, so I'll just mark the flow of Ix to be something like this. It's all clear? So these are the three set of rules that we are going to use in order to compute the output impedance, and later now we'll just use that in order to compute it. Have you made a note of this, all 3 points? These 3 points are more important. Now the circuit that I'm talking here is basically the small signal, okay, so small signal model of the entire circuit, okay. So I'm going to use the small signal model and then I do all those 3 steps on it. Clear? Huh? Vin is an AC source, so again I'm going to consider that as an independent source. It's not like something like a voltage controlled current source or something like that, okay. So though any independent sources has to be killed apart from this Vx that we are applying. In order to draw this small signal model, we will suppress all the DC sources, but Vin will be there. But whenever I try to identify an output impedance, that time I have to kill this input source, okay. So that is how we can compute the output impedance. Yeah, so now we'll just begin some exercise. So what I do is that I'll just give some set of circuits and I just want you people to use this in order to compute your output impedance Rx. Okay. Yeah, so here is a very simple circuit. I'm going to assume that the lambda is not equal to 0 and I just want to figure out what is the impedance posed by this particular circuit at this particular node. Now what I do is that first thing is I just need to translate this entire circuit into a small signal model, okay. So first let me draw the small signal model. So where I have the gate, drain and the source, all these 3 nodes would be marked over here, okay. So the gate, drain and the source. So now what is happening is that I have some sort of Vin or Vg that is connected. So this is a composite signal, and this composite signal, when I translate to my small signal model, what type of signal I will end up having it? Can I carry the entire composite signal to the small signal model? Yeah, only the AC signal component I need to carry in, right? So I have the small VGS or VG, okay, and I can also define some polarity here because the polarity is important for us to draw the current small ID, right? Yeah, so now that I've just used this positive polarity of my signal, and I also mark the other nodes where it is connected. So I have this source which is already connected to the ground, so I mark that with the ground, and later on based on this VG polarity I'm just going to draw a current source, and it flows basically from drain to source just because of this polarity, okay, and whose value is Gm times Vg. Now apart from this, since because I have this lambda that is not equal to 0, what happens is that it leads to some sort of resistance here whose value is R0, okay, and this is a small signal model that I have for the given circuit. Now the step here is that I just want to evaluate the output impedance of this circuit. Now what is the very first step that I need to do? Step 1, okay, with respect to the output, what I supposed to do, or the node at which I want to figure out the output impedance? Yeah, apply the voltage source Vx at the point at which I am trying to figure out my impedance, okay. So this is the drain through which I want to find the output impedance. So what I do is that across the drain I am trying to connect a voltage source with some polarity like plus and minus, okay, and then the second step was to kill any independent sources. So in this case the only source that I have is this Vg, and one could even model as a kind of voltage source here, okay. So then now the point is that I need to kill this guy. So what I do is that I just bring this node to the ground, okay. Now what happens the moment I do the second step? What happens to this current source? So this is a small signal current ID, and whose value is basically depends on this Vg. Now the value of Vg is right now is equal to 0. Now what happens to this current then? the current is also equal to 0. How will you represent the current? It's an open circuit. So what I do is that I just open out this particular point. Okay, so I've just created an open circuit between the node of source and the drain. Okay, now what is left over is just the R0, and now how will I measure the current Ix? So I just place an Ix. Okay, now I just want to evaluate the expression for Vx. A voltage is nothing but the product of a current and a resistance. It's as simple as that. Okay, so the current that flows through this resistance would get me the value of the potential drop across this R0, right? Yeah, so that value is exactly equal to my Vx. So due to which I can write it to be equal to Vx is equal to Ix times the of R out. Right? Now that I just want to evaluate the value of Rx, R out, okay, and that is equal to Vx by Ix, and when you do so, you would end up having a value of R0. Okay, so we got the value of this to be equal to R0. Any doubt in this? Shall we move on to the next one? Yeah. So how do we compute the output impedance of this second circuit that I have plotted here? R0 parallel 1 by Gm. Why to get confused? Why not we draw the small signal model and then perform the same analysis that we did rather than guessing? Because the answer is not that. Okay. So what I do is I'll carry the circuit to the next page. Now what I do is that I just try to draw the small signal model. Now when I look here, I just plot all of these three nodes. Okay, so that is my general way of doing the small signal model. So this is my gate, I fix my source here, and the drain is here, and I have this VG. And what happens to this VDD when I translate to my small signal model, which is connected to the source? Yeah, that is grounded, so I have this. And in general, we always try to measure the polarity difference between the gate and the source. It is not between the gate and the drain. So due to which I will just mark the polarity between the gate and the source terminal. Okay. And here is the drain, and through which I try to figure out, I want to find out the value of Rx. Okay. So now that just because of this polarity that I have defined for my voltage between the gate and the source, how will I draw the current direction? Drain to source or source to drain? It's a PMOS, right? Should I need to draw source to drain? No. In the last class what I said is that for small signal model there is no difference between a PMOS and NMOS. It is the same. Okay. Only when it comes to DC we have to think about whether it's a PMOS or NMOS. Okay. So in this case it doesn't matter. It only depends on the polarity of my VGS, nothing else. So in this case the polarity of the source is the least potential, due to which the current flows towards the lowest potential in my circuit. Due to which I will just draw something like this, and it is written as Gm times that of Vg. Okay, and what is left over is just the R0. Okay, that also I fix it. We'll try to figure out the output impedance at the drain. Okay, so in order to do so, the very first phenomena I have to do is to connect my Vx and then kill the input source or independent source. So it could be done by connecting this gate to the ground. So due to which the VGS right now would then become 0, and when I have VGS that is equal to 0, then the current would obviously goes to 0, and one could represent the current being 0 by an open circuit, due to which I open out these two nodes, and again I have to put a current that is flowing here, right? So the current that flows is measured as Ix. So now what is the end result of this? Yeah. Okay. So in short, the final conclusion that I can get it here is that whenever I have a drain terminal, the impedance that I am going to look in will be R0. Okay. But I will hold this particular statement for a while, but after then I will break this particular statement by adding some extra element to it. Okay. So as of now, whenever I have when I am looking for an output impedance at the drain terminal, the output impedance that I would see is R0. Okay. So this is with the caution I am telling. It is not always. It is with the caution I am telling. Okay. Yeah. So now we'll just move on to a different type of circuit where So I just need to find the output impedance of this particular circuit. I think the answer of this was already given by, yeah, but let us not reveal that. Let us make you people to derive that. Okay, so how would we do this? Okay, so I again begin with drawing the small signal model with starting with all the 3 points of my gate, source and the drain. Okay, so and right now according to the circuit that has been given here, the drain is available at the bottom and that has been connected to the ground. So I just connect directly that node to the ground, and what is connected over here is just VG, and I'm going to consider a positive potential across the gate such that the source will become a negative potential. Okay. Now how will I draw the remaining part of the circuit? So again there is a current source, right? Yeah, it will be the current from drain to source, just because it depends only on the polarity, right? So because the source is the least polarity in my circuit, what I do is that the current has to flow towards the least potential. So that's the reason why it flows from the drain to source, and whose value is Gm times that of Vg. Or if you want, you can just write it as VGS in case if you are getting confused. Okay. Now we also have one more component, just because the lambda is not equal to 0. So due to which I place a resistance R0 along with it. So this completes my small signal model. Okay. So now to this, what I need to do is that I just need to fix a voltage in order to find the output impedance. Okay. So that voltage has to be fixed at which terminal? To the source. So I just go and connect my Vx with plus and minus, and also one more thing that I need to do is that I need to kill this Vg. Okay. So what I do is that I just connect the ground towards the gate towards the ground. Okay. So and it is left over with something like this. Okay. Now I also have one more thing, that I need to measure the value of Ix. Now what happens to this VGS? Is it currently goes to 0? No. In case if you have a doubt, you can always write this VGS as something like this: Vg minus Vs, and see what is connected to the gate and what is connected to the source. So what is connected to the gate? It is 0. So I just fix a 0 for this. But what is connected to the source? No, we will not consider negative or positive as of now. What is connected is a positive voltage of Vx. So I substitute that value over here. Okay. So this VGS in turn becomes a negative value of Vx. Okay. Now is my VGS is equal to 0? No, it is having some sort of value. So whenever I have some value, then what happens to the current? Will it be a 0 or some current flows? Yeah. So we will not worry whether the current exists or not. That's the question here. Obviously VGS is not equal to 0, due to which the current exists. Okay. So I no need to take off this current source, and that is the logic. Okay. So let us try to look for this Ix, and later we'll substitute the corresponding value of VGS using the Vx. Okay. Yeah. So now how will I write this current Ix? Yeah. So what I can do is that I can sum both these components, or you can do the other way if you want it. Okay. We will put it in downward or upward. Okay. So we'll go with the downward one. Okay. So this current in general splits across these 2 points, so that I can write this current as something like minus Gm VGS. And how do I write the current that flows through this R0? Yeah, so it is nothing but the potential drop divided by the R0. Okay, so due to which Vx by R0. Okay, and now that I want to replace this VGS with something that is related to the Vx, right? So we already had expanded this VGS in terms of Vx, so I use that such that it ends up having something like Vx, or I will just bring this Vx out in common, and I have something like this. Now what is Rx? Rx is nothing but Vx by Ix, and due to which I have something like by Gm into R0. Okay, so the output impedance has become R0 divided by 1 plus GM R0, and this combination is pretty simple. One could even further simplify this expression as something like R0 in parallel with 1 by GM. Okay, this is more important for us. It's always better to visualize the impedance that I'm seeing across the source as something like this, okay, as R0 goes in parallel with 1 by GM. Okay, are you clear with the conversion from here to here? It's a pretty straightforward way of expressing that. So what happens if I'm going to assume that the lambda is equal to 0 for the circuit? What will be the output impedance? It will be 1 by GM. Okay, so hope that everyone is clear. Now again I will just come up with one more circuit, and let us try to quickly answer this. So what is the output impedance of this circuit? Only you are telling. Where I am looking at it? I am looking into the drain or source. Source. So what's supposed to be the impedance? Yeah, it's supposed to be the same. Whether we are working with the PMOS, this is an NMOS, or in the previous case we worked with a PMOS. Okay, so in both the cases we have to have the same result, just because the small signal model is same for both PMOS and NMOS, due to which the output impedance also has to have the same relations. Okay, so whenever we look into the source terminal, I will have this kind of expression. Okay, now again it's with a caution I'm telling that when I add some other element, then this relation would then break, but we will hold that particular concept to come after this. Okay, yeah. Now there is, let me mark this as 4, and the fifth circuit would be I forgot one more thing in the topmost circuit. What happens if the body is connected basically to my ground, or in this case the body is connected to my VDD because it's a PMOS? We didn't address these two issues in this small signal model. Okay, so let us try to map this VDD onto the small signal model. So what happens when this body is getting translated to my small signal model? It goes to an AC ground, am I right? Because it's a DC source, VDD is a DC source, so that when I translate to my circuit, the body would then goes all the way to the ground, AC ground. Okay, so now I'm just comparing a potential difference between the body and the source. Is there any potential difference? Yes, because body is at ground, but the source is at the most negative potential, due to which there is a VBS. Okay, now whenever there exists a VBS, how will I draw the current direction of it? Which is positive and which is negative in this case? The body is higher potential than compared to the source. Okay, so from where to where the current has to flow? From the drain to source or from source to drain? It is from drain to source, because source is the least potential in my circuit. Okay, so the current, if you are getting confused, it's pretty simple. Whatever the current direction that you use for this GM VGS, use the same current direction. Okay, that is the shortcut way that I can tell. Okay, so I have to add somewhere in the circuit. Yeah, so now let us try to deal with this. I want you to compute for this. Now this current Ix is not only two components that I wrote before, but it also has the third component. The current branches even in this particular path. Oh, sorry. It's a good sign that you people found some mistake. Yeah. So I have an extra third component. So what should I need to do? I have to add one more expression to it, right? So what is that expression? What is this current? It's minus GMB times VBS. That's it. Okay, so what I do, again I have to give some enough room. Sorry, it's a negative sign. Okay, so this is an extra term that has been added. So the only thing that I need to further do is to find what is this VBS expressed in terms of Vx. So I do the same split up, VB minus Vs, where I could find that the body is connected to the ground, so due to which this goes to 0, but what is connected to the source is nothing but my Vx, and ultimately I will end up having minus Vx for this Vbs, and due to which when I replace this Vbs with minus Vx, I would get a positive sign at the beginning, and Vbs would be replaced with this. Okay. Now this entire expression, yeah, okay, and again I will write this. Okay. Yeah, sometimes it becomes very difficult for me to write as Gm plus GMB. So in order to express this, I sometimes use this as Gm prime, okay, which means it's a summation of Gm plus GMB. So whenever I find something like that, I just replace that guy with Gm prime. It becomes, my life becomes easier, okay. So over here I just replace with Gm prime, and over here again I will replace with Gm prime, okay. Or if you really want to express not in terms of Gm prime, then I can further write this as R naught in parallel with 1 by Gm in parallel with 1 by GMB. Is that is clear? Any doubt? No? Can we move on? Okay. Yeah, so now that we'll just come back to this where I need to find out the value of Rx, and this type of circuit is also called diode connected transistor. Okay, so it's a diode connected structure. Okay. Now for this circuit I just want to find out the output impedance. So since because I always get excited, I tend to draw all the small signal model and do by myself, but that will not make you to think. So I will stop here. I want you to write down and give me the result, and later I will work out this particular circuit. Is there any doubt? Shall I redo the same? I'll just redo the same just for the sake of this recording. Yeah, so first I try to draw the small signal model of this. So I just pick my source. This is my source potential which is connected to the ground, and there is a drain and there is a gate, and this gate is actually shorted to my drain, and I'm just trying to fix my polarity between the gate and the source with plus and minus, due to which the current would flow from the drain towards the source whose value is Gm times VGS. There is an R naught. Okay, so this completes my small signal model. Now what I do is that I just try to fix the drain with Vx, with plus and minus. Okay, now I just want to express this VGS in terms of Vx. Okay, so I just try to do VGS as Vg minus Vs, and the source potential is already grounded, so I fix a 0, but what is connected to the gate is nothing but my Vx. Okay, so the entire potential is right now is equal to Vx. So now this current obviously flows, the Ix is flowing through two paths. Okay, one is this particular path, the other one is through the R naught. But can there be a flow of current through this particular path? No, just because it's an open circuit. Okay, very high input impedance in this case, due to which no current would flow through this path. So I write this Ix as summation of Gm VGS plus the current through this, which is Vx by R naught. Okay, so I know the value of VGS is nothing but Vx, so I just substitute that over here. It becomes 1 by R naught times Vx. Okay, so from here the value of Rx is Vx by Ix, and that is nothing but the same phenomena. Okay, we'll just move on to the next one. So find the output impedance of this circuit. Think whether we will get the same answer or a different answer. How many of you people agree that we'll end up having the same answer? Okay, 1, and here one more voice. Okay, 3, 4. So everyone else is telling that it is a different answer. So get me the answer then, if it is different. I will also stand with the second option of not being equal to the same as we had before. Okay. I think we are running short of time. Okay, I will also try to do, but don't look into the answer right now, whatever I'm doing it. You try by yourself. Now in this case, there is a potential difference between the gate and the source, so I just substitute here. This is the complete circuit. Are you clear with this circuit that has been drawn? Just because there is a potential difference between the source and the body, okay, we have one more extra current that is flowing, okay, which is GMB VBS. So the polarity and everything remains the same as that of my VGS. So the only thing is that this IX has to split into 3 components. Okay, one is this component, the second one through R0, and the other one is GMB VBS. So I write this current IX as a summation of minus GM VGS, and then the current through this guy is nothing but Vx by R0, and the current that is flowing in opposite direction to GMB VBS. All of these 3 current components have been written down. The only thing right now is left over is to express this VGS and VBS in terms of Vx. So what I do, I just do the same principle of following this VG minus Vs and see what is there inside each of them. Yeah, so in the case of the gate is connected to which terminal? To which potential? It is drain, and the drain is again connected to the ground. So I have this guy that is equal to 0, and the Vs is actually connected to a positive potential Vx. Okay, so due to which I substitute this one for my VGS. So what I have is minus Vx. So the same principle could be applied even for VBS. I would end up having the same result. Okay, so both my VGS and VBS has the same relation with respect to my Vx. So I just substitute here, or I will pull out this Vx in common. Okay, and this is supposed to result in Rx, which is Vx by Ix, and the end result is nothing but Gm prime in parallel with R0, and Gm prime is nothing but Gm plus Gmb. Okay, so hope that everyone is getting this answer. I just want to cover 2 more circuits. Yeah, so find the output impedance of this circuit. So what I do is that I just try to translate this entire circuit into a small signal model first. So I have my gate, and then the source, and the drain here, and across the source what I have is a resistance whose value is Rs, and across the gate what I have is VGS or something like this. A VG is there. Okay, so since because the value of VGS is not equal to 0, and I have a polarity of plus and minus for the gate and the source, I just draw the current direction from drain to source, whose value is Gm VGS, and we also have to worry about the body effect. So again, the body effect will follow the same polarity of my VGS, so I just draw the current direction of that, GMB VBS, and one more thing that is left over is this R0, and all of these nodes are connected to my drain. And this is a complete small signal model that I have, and now to this I just want to apply my Vx, measure Ix after killing the input source, so such that we will end up having some sort of result. Okay, so first I will begin with the step number 1. step 1 is to fix a voltage source Vx across the node at which I am trying to find the output impedance. Okay. The second step, kill the source, independent source. So in this case, the Vg is the input source, which I just kill it here. Okay. So I have connected the gate potential to the ground, and the third step is nothing but measure the Ix. Okay. Now the point is that before I even start writing this Ix expression, I just want to figure out whether the value of VGS exists or not, right? Is it a 0 or not equal to 0? It is not equal to 0 just because the source is currently not at ground. Okay. So let me expand this VGS as VG minus Vs, and let us assume the same Vs itself. Okay, so let me write it. So what I have here is a 0 and then Vs, and due to which I have minus Vs here. Similarly, I can even write the expression for VBS to be exactly the same. Okay, so I have this VGS and VBS sharing the same relation with respect to node Vs. Okay, or this potential. Yeah, due to which both these current sources would exist. And now let me try to write the current Ix over here. So again, how will I write the current expression Ix? This current is splitting into 3 parts. Alright. So the first current is nothing but GM VGS. The second current is GMB VBS. And the third current, yeah, how will we write this? Is it Vx by R0? Just Vx by? Huh? Yeah, one way is doing that, but I feel, for me, this feels to be a better option. You can do it in any different way. You can even perform the source transformation, do the same thing, that is also fine, but I need the end result to be the same. Okay. Yeah. So over here, there is a potential difference between these two guys. So the highest potential at this point is Vx, and the lowest potential I'm going to consider as Vs. So due to which I have Vx minus Vs divided by R0 is the current that flows from drain to source. Okay. Now again, I'm going to replace each of these VGS and VBS with minus Vx. So I just replace them. So I end up having something like this. Okay. Now we want to express this, even the value of Vs in terms of either Vx or Ix. Otherwise, the circuit or the expression will not loop around to get us Vx. Huh? How? That is what we have to find out. This VGS is nothing but the gate is connected to the ground. Oh, sorry. Yeah. Exactly. Yeah. Sorry for that. So what expression could be substituted? Yeah. The same current would then get merged across this node, and what current flows at this Rs is the summation of all the 3 components, and what is the summation is equal to Ix. So what I have here is Ix that flows this through the Rs in order to get the value of Vs. Okay. So the drop across the resistance produces me the voltage Vs. Okay. So I can just go around and then replace each of these guys in terms of Ix Rs. So again Ix Rs. Okay. So I'll just need to pull out each of these terms, including this, towards the right, so that what I have is 1 from here, and then GM Rs, GMB Rs, and one more term from here, which is plus Rs by R0, and the whole of these things has to be multiplied with Ix, and the leftover term is just the Vx by R0. Okay. So now that when I put them like Vx by Ix, I would end up having something like because these two terms are common, I just put it as Gm prime, okay, combining both Gm and GMB, and then I have this Rs by R0, and this is what I have. And now I'm just going to bring in the term of this R0 inside this parenthesis, So okay, so now one could see that the middle term that I have written, which is Gm prime Rs R naught, will be much larger than compared to the value of R naught or Rs, right? So due to which one could approximate, depending on the condition, one could approximate this entire expression as Gm prime times of Rs times R naught. Okay, so there is something that I want to emphasize here is that whenever I have a source resistance Rs, and when I look through the drain, the resistance Rs is being magnified by a quantity which is nothing but Gm primes thereof Rs. In short, the Gm times R naught has a specific name. What is that? Intrinsic gain. Okay, if you could able to at least think over it, we can actually bring out this expression in a much easier way rather than doing all this expression and then calculating the final result. One could say that whenever I am looking through the drain and when there is a source resistance, this source resistance would be magnified by a quantity of Gm times R naught, or the intrinsic gain of my transistor. Okay, so now I'll just take one more minute, just a guess, but I will prove this in the next class. What happens in this case? I have a drain resistance, but I'm looking through the source. What happens to this drain resistance when I look through the source? In the previous case, I had a source resistance, and when I look through the drain, this source resistance, Rs, was being magnified by Gm R naught times that of Rs. Okay, it was being magnified when I look through this drain. But right now I have swapped both these conditions. Okay, so I have placed my drain resistance and I'm looking through the source. Now what could possibly can happen in this case? A simple guess, wild guess. Or here it is magnified. What could happen possibly here? Diminish. Okay, so an approximate output expression for this is nothing but the RD would be reduced by this quantity. But again, it is not exactly intrinsic gain. It is Gm prime, where Gm plus GMB has to be included in both the cases. Okay, so with this I will just stop, and the proof of this I will do it in the next class.